hit the show on the road here. So, yes, we have an exam coming up next week. And we will have a short review. Of course, I have my office hours as well. So, again, the exam covers the materials through lecture notes number 7 that we completed yesterday, or last lecture, sorry, Tuesday, and through the problem set. So I'll have those solutions out graded as soon as possible. All right? Okay. So, after a month plus of establishing the foundations of quantum mechanics, what we're going to do now is try to put the mechanics back in quantum mechanics. We haven't really talked about mechanics, physics. We have this information theoretic foundation that we've established, but the hook back to the physical world, that's what we're doing. That's what we're going to do for the remainder of our semester. So I'm fond of this quote from Asher Paris, who's one of the great thinkers about foundation of quantum mechanics. He was fond of saying, I think roughly, quantum physics happens in the lab, it doesn't happen in Hilbert space. So we want to have a hook back to our space, our physical world. The Hilbert space is abstraction, so there's a hook that connects these things together. And I think the best way to think about it is based on Noether's theorem. So, and we'll Noether derived this theorem from Lagrangian mechanics, but it follows generally in all of physics that if we want to think about space and time, we want to think about the symmetries of space and time. And associated to every one of those symmetries, symmetries that are so-called continuous symmetries, that's to say they're described by Lie groups, and we'll roughly explain what that means. Then every one of those symmetries is associated with conserved physical quantities. We have conserved quantities in the world because there are symmetries. Okay? So the reason that energy is conserved is to the degree to which the laws of physics are time translationally invariant. Okay? So time translation is associated with conservation of energy. And what Noether's theorem tells us is that those conserved quantities are the generators. So that term we want to define as well. Other symmetries are, we might have translational symmetry, space translation, or the isotropy, the rotational symmetry of space. That's associated with conservation of angular momentum, and that tells us that angular momentum is the generator of the group of rotations. Okay? So the hook between this space-time symmetries of the world and these physical quantities is through Wigner's theorem, which we'll derive next semester. Basically, what Wigner's theorem says that all symmetries in quantum mechanics are unitary maps. So there's our connection between the Hilbert space and the lab. It's through symmetries which have a space-time physical space interpretation and unitary maps which happen on Hilbert space. There's our hook. And so the mathematics, just the very basics of it is that we're talking about symmetries. The set of symmetries form a group, and groups are sets that have a a composition law. That composition law is associative, and it has identity elements and inverse elements. And we can represent the elements of the group as through unitary operators. So for every element of the group, there's an associated unitary operator. Okay? And this is a representation of the group in that the composition law is just the matrix multiplication, or the operator multiplication. So take two operators, multiply them together, that's the same thing as the operator that you would get if you did the group composition law. Yeah?
This may seem like a stupid question, but if you said you have time translation symmetry, could that system not have space translation symmetry? Or
yeah, I mean, we could have a circumstance where, we have walls here, and if we combine ourselves within these walls, this is not completely spatially symmetric. If I go over here, it's different than over here. Well, of course, what that means is the momentum is being taken up by the wall.
So one symmetry can preclude any other symmetries?
Not preclude, but they're independent symmetries. You don't have to have all of them. But to the degree to which the overall universe is spatially the same, as the laws of physics are the same in all parts of the universe, and there's no special direction of the universe, and the laws of physics are the same at all instant time is the degree to which these are considered quantities. Okay, but as I was saying, those symmetries are the set of symmetries, the set of things that perform, let's say, a time translation are a group, and we can, through Wigner's theorem, say that that group is represented by a set of unitary operators. And this is the fact that this is a representation says this, okay? And that the identity element of the group is the identity operator, and the unitary associated with the inverse element of the group is the inverse of the operator, which of course, if it's unitary, is the dagger, okay? And so what we're talking about now is time translation. That particular symmetry, which is dynamics, okay? And so we have the group here, let's say, so I have time translation operation or elements, and they are this set of all times, okay? So this is everything that translates by some amount of time is defined by the time at which I'm translating it, okay? So this set, of course, is a continuous set. It's the real line. This is what makes it a Lie group, is that the set of elements of the group form a smooth surface. In this case, that surface is the one-dimensional line. Okay, that's what makes it a Lie group. The manifold, more precisely. And the composition law here is just if I have two time translations. Well, that's just I translate this addition. So the composition law is addition. And the inverse, if I want to go backwards in time, I just have the minus sign. Okay? And the identity element is what? 0. That side over. Let's call it 0. Okay? That means if I add no time to it, I haven't changed the translation at all. Okay? So we're going to translate relative to some fixed time. So we're going to say if I want to translate in time from, bless you, some time t0 to time t. So really I have to say what my initial time is. Okay, so my element of the group is represented by a unitary operator which takes me from t0 to t. So this is the time translation operator that translates me from that time t0 to the time t. All right, so this is my element of the group. And we also have this composition law, which I can write in the following way. Suppose I go from time t0, what's I want to say here? I can write the following thing. So here's a composition law, which says I translate from t0 to t, and then from t to t1. That's the same thing as translating from t0 to t1. If t is between t0 and t1. All right. So now what's special about Lie groups is that they're continuous. And because there's continuous, there's a sense of differential calculus. That's what's important here. Which means we can talk about infinitesimal translations or infinitesimal elements of the group. That is to say, there's a notion of a near identity element of the group. Okay? So, what I mean by that is the following. So, the identity element was, if I have this is the identity element. I don't do anything, right? Translated by nothing. But if I go to t0 plus some dt, some very small differential, well, this is something which is equal to some anti-unitary operator that's a function that's proportional to dt. This is anti-unitary. Why does that have to be anti-unitary?
The composition law to work?
Well, the composition law would work if that's a linear operator. So it's got to work, that's for sure. It's got to be linear, otherwise the composition law won't work.
So
But it's got to be a unitary operator.
So
right?
the terms cancel out?
So it's got to be the case that U dagger U is the identity, right? And what is that? Well, U dagger, if this is, that becomes A dagger. And A dagger is minus A, because this is excuse me, anti-Hermitian. Excuse me. Pardon. So if this is anti-Hermitian, when I take the dagger of it, I get minus A, right? And this is then 1 plus dt A. And that's equal to, the cross terms vanish. And then I get a dt squared, but order dt squared is 0 if this is a differential. Okay? So this, in order for this to be a near identity unitary operator, it's 1 plus something anti-unitary. Okay? And this thing is the generator of the group, because it allows me to move away from doing nothing. It generates the transformation. Now, if it's anti-unitary, we can always write it as I or minus I under Hermitian operator. And in this case, since this is time, it has units. That thing I'm going to call omega. So the anti-Hermitian operator here is minus I times a Hermitian operator. It has to be. All right. And as we discussed then last time, from Noether's theorem, energy is the generator of time translation. So that means that the generator must be proportional, the Hermitian generator must be proportional to energy. So it's some proportionality constant times the energy operator. And the energy operator we always call the Hamiltonian. And that we argued last time that this is some constant of the universe that has to have the units of energy 1 over the constant has to have the units of 1 over energy times time, right? Because U, for this differential math, this constant alpha has the units of 1 over energy times time, because this is dimensionless. And that constant H. So what we have thus is that the generator of time translation is the Hamiltonian, and you can write that, bless you, as if I go a small distance from T0, that's the identity minus I times the Hamiltonian dt over h. So we want to solve for this time translation operator. Right now we have it as this in differential. That means we can write down a differential equation. So let's say I want to, so I seek this map, the map that takes me from t0 to some finite time t. Okay, that's what I want. I have this. The way I can now have a differential equation for that. The way I do that is the way in which the differential equation, which says how this changes in time, just from calculus, is I take a small delta t, I translate it by a small amount, subtract what it was before I did that, and divide by delta t. That's the definition of the derivative. And what is this? Well, aside, so this guy, when I translate it by a small amount delta t, according to the composition law, is this, right? First I go from t0 to t, and then I step a little delta t, right? And this is a near unitary map. I'm sorry, near identity map. It's very close to identity. I'm just stepping by a little delta t. So this is 1 minus I over h bar, the Hamiltonian delta t. So, let's plug that in over here. I plug that in. This is, let me do it over here. Just factoring this out, I plug this in, and I factored it out. I get that. And this, plug in. Right? And when we plug that in, and we put those together, what we get is this is equal to minus I over h bar, Hamiltonian times u. And this is what we call the time-dependent Schrödinger equation. This is one form of the time-dependent Schrödinger equation. The first time we mentioned the name Schrödinger, Kitty. But here he is. So the Hamiltonian is the generator through this differential equation. Often this is written with a partial respect to time. It doesn't really matter here because there's no other variable. But when we get to wave mechanics and we introduce position and as well as, or momentum as well as time, then often we have to emphasize that with other partial. So I'll just rank that way here. It doesn't make a difference. All right, so what is the solution to this equation?
Depends whether or not, which depends on time.
It does. So right now, let's say this is just an operator that doesn't depend explicitly on time. I have to come back to what the heck that means anyway. Because this is the generated kind of translation, so why not we have h dependent time? But let's, so h, given h, assumed independent time, what is the solution to that differential equation? Exponential. So, the solution, u is equal to the exponential of what?
Negative I bar each term operator rates.
Yeah. But what about time?
Times t.
We got t0 here, though. So we have to have when we have a differential equation, we always have to think about the initial condition.
Would be t minus t0?
It would be, because at time t equals t0, this has to be the identity. Okay? So that's the solution. How do we know that's a solution? Well, we could check. How can we check that? One way to check that is to think about this as a way we discussed, hold on a second, as the way we discussed in the homework where we looked at functions of an operator. We can look at this as a power series. Right? Over n factorial. And then just take the derivative of this. And when you take that derivative, it works. Yeah, Stephen, you had a question?
You answered my question.
Yeah, okay. All right. I want to make one point here that every unitary operator, u, is the exponential of some anti-unitary operator. Or I can write it equivalently as minus I times some k, where this is, oh God, I'm saying that, anti-hermitian. Sorry.
Are you trying to give spoilers to your next lecture?
What's that?
You keep saying anti-unitary. Is that something we don't know yet?
No, it's because symmetries can be either unitary or anti-unitary, and that's just stuck in my head. These are well, I think it's, we could show it one way. If I have an operator of this form, and I take its adjoint, what do I get? Either plus ik, right? Because k dagger is k. And that is u dagger. Okay? So these are my unitary operators, and the things in the exponent are the generators. All right, so now it was alluded to the question, what if H itself is time dependent? What would that mean anyway?
Can you solve it with the exponential of the integral then?
Yeah, so well, first of all, I want to just say something about the physics part. Suppose the Hamiltonian is an explicit function of time. It's a little bit of a weird thing anyway. What does that mean? How could that possibly be? Yeah.
Maybe it's the magnetic field changed in time?
Right. Good. It's a good example. When we have a Hamiltonian as a function of time, what that means, say, for example, as he suggested, the Hamiltonian is a functional of something like, for example, a magnetic field. And that magnetic field itself is a function of time. Now, this is a little bit weird. And I want to explain why I say this is weird. Because what this is saying is that the Hamiltonian is a function of some variables which we're taking as classical variables. We're taking this as a classical field. We are not quantizing the magnetic field here. We're treating the magnetic field as a classical parameter, which is explicitly a function of time. Okay? Now, when you can do that and when that's fair is a very subtle and deep question. We're not going to get into it for a little while. Maybe not ever this year, but we'll try. But for the moment, we have, when we control quantum systems, we shine laser beams on them, we shine microwaves, we put beads on semiconductors and put currents, and we treat those variables as classical fields. And that's how we drive the system. So in some sense, it's an open quantum system, right? But it's not open in the sense that we talked about last time, where we treated the environment as quantum degrees of freedom. This is classical degrees of freedom. So this evolution is still unitary, especially if this is deterministic. I mean, if the magnetic field's a little bit noisy, well, then we lose some information, right? But to the degree to which we know what this field is and we control it very well, this is still unitary evolution, even though we are interacting with it from the outside.
There's a way in the control panel.
Very subtle points. Okay.
Windows updates and you say,
All right. So given that, with that said, we just have a piece of mathematics now. We say my differential equation is that du dt is equal to minus I h bar, the Hamiltonian, which is now itself some time-dependent operator. The operator itself is a function of time times u. All right? So now, how are you going to solve this one?
Power series.
Yeah, we can deal with the, we could do that same power series again and try to put it in, but I can't just make that ansatz. Let's do a little aside. Suppose I have the following thing. Suppose I have a classical function. Which is some qt. What's the solution to that differential equation? How do you solve it?
Divide by f of t.
Yeah, exactly. So I can,
Oh,
I could say this is the f dt over f of t times g of t dt, right? I then integrate this from, say, t0 to t, make this a t prime because it's a dummy variable now, right? And then this, the left-hand side here is the log. Is equal to this integral. Right? And so then if I then exponentiate that, I get that f of t is f of t0 times the exponential of that. Okay? So I could just say, well, let's just try that as the solution to this. In this case, that would say that u at t and t0 is u with, well, that at time t0, that's the identity. And then I have e to the minus I over h bar t0 to t dt prime, the integral of the Hamiltonian. That would seem to be the generalization of what we wrote over here as the simple case where h were time independent, right? So let's check that in the same way. Let's write it in terms of the power series. Okay, so as a power series, this is equal to the sum over all the powers times right over n factorial. That's just expanding that in a power series. But there's a real problem here. Because when I write, let's look at, for example, let's write out the first few terms. So this is equal to 1 minus I over h bar dt prime. And then I have plus a half over h bar squared integral d0 dt double prime right? That's okay so far, but if I try to take this derivative, I'm not just going to get the same thing one power down, because there's a question of what order is this in. The question is, does this operator commute with this operator? If they commute, I can take the derivative, it'll be perfectly fine. But if they don't commute, check for yourself, I won't get back this. I only get this if they commute with one another. So this is only the solution. when the Hamiltonian commutes with itself at different times. And this is why actually solving for the time evolution of quantum systems is hard, and why we need Feynman diagrams to solve for, you know, or density functional theory, or whatever. This is a very hard problem. So we'll come back to that next semester when we talk about time-dependent perturbation theory. This is only the solution if they commute with each other at different times. All right, very good. So that's the general solution, but often instead of just solving for the whole time evolution operator, we just look at how the state itself evolves as a function of time. Hamiltonian dynamics of the state. How are we going to do that? Well, the state, let's just consider a pure state. Or almost always for the rest of the semester talk about just pure states. We have the state at some time t. We can think about that as the propagation from time t0 to t. That's what the time evolution operator does. It takes you from time t0 to time t. Okay? So now I want to look at how does this thing evolve as a function of time. So to do that, I'm going to solve for a differential equation. Okay? And that is equal to the time derivative of that. That's the only thing that depends on t. And this, we say is generated by Hamiltonian. For the moment, let us again just take we'll consider time independent Hamiltonians pretty much from now on. So this is equal to, right over here, minus I over h bar, the Hamiltonian, the time evolution operator, acting on that. Okay. Just plugging in what we have. And this is sine t. So we have another form of the time-independent Schrödinger equation. Says that the way in which the state is changing as a function of time is given by the Hamiltonian acting on the state. Now, time independent, time dependent. By the way, what if we wanted to write the time evolution for an arbitrary state? It'd be mixed, according to Hamiltonian dynamics. How do we do that? So we want the Schrödinger equation for the density matrix. lots of ways to do it. Anybody have any suggestions? Yeah.
Can we maybe try to take the adjoint of this equation?
Sure, we could do that. So we could just say, for example, this guy is a statistical mixture of states. This is one way to do it, for sure. And there's the adjoint, right? I take the partial derivative of this. So that's the partial derivative of that times that plus this times the partial derivative of that using the product rule. Buy it? And this is that, and this is the adjoint. And the adjoint is, all right, it's got a plus I. The Hamiltonian is Hermitian operator, so I don't have to, so it is equal to its own adjoint. Okay? So this is equal to, I can factor out the Hamiltonian. This is the Hamiltonian, or I over h bar with a minus sign. The Hamiltonian acting on the density operator. That's this first term, just taking it out. And then I can take the Hamiltonian out the other way. Right? And so what we have is that the partial derivative with respect to time of rho is equal to minus I over h bar, the commutator of the Hamiltonian with rho. This is another form of the time-dependent Schrödinger equation. This is Hamiltonian evolution of the state, but it could be initially mixed. This preserves the purity, preserves the entropy, because it's unitary. Right? Note, this is not the Heisenberg equation of motion. We're going to, maybe you've seen that before, the Heisenberg picture. We're going to talk about that next lecture if you've seen it. This is the state. And the state evolves. All right, so now, of course, once we are wanting to solve the Schrödinger equation, there's this very special set of states that play a very special role. And those are the eigenstates of the Hamiltonian. We care about them because they are the thing that tell us all about dynamics. So, in dynamics, special role of the eigenstates, or eigenvectors of the Hamiltonian. So, the Hamiltonian is a Hermitian operator. Hermitian operators have energy levels. Or energy, Hermitian operators have eigenvectors. And those, let's call them U. This is the energy eigenvalue. we know they're real numbers because this is a Hermitian operator. And the eigenvalues of any Hermitian operator are real. We don't know whether they're positive or negative. This is not necessarily a positive operator. And the set of possible eigenvalues can be anything, any real number at this point, unless we know something more about the nature of the Hamiltonian. And these states, or this equation, is known as the time independent Schrödinger equation. Now, for many physicists and quantum chemists, this is all quantum mechanics. The rest of it that we've been doing, I never think about it. I just want to solve the Schrödinger equation for, you know, some big molecule or some solid state material. Of course, this is a piece of the story in quantum mechanics, but it's not the whole story. But it's an important part because it tells, once we have the energy eigenstates, then in some sense we can derive everything about dynamics. First of all, let's say one thing about what's one thing that's special about the energy eigenstates. Suppose at time t equals 0, the state of the system is one of the energy eigenstates. Let's suppose that's true. Okay? What is the state of the system at a later time? Well, that's given by the time of minute. From now on, I'm just going to let me take t0 so here t0 is time to 0. Okay? So according to the rule, we translate this state in time according to our unitary translation. And this is equal to e to the minus I over h bar, the Hamiltonian times time. Times that. So what is that? The Hamiltonian, these states are defined as eigenvectors of the Hamiltonian. So when I act this on this, what do I get? H acting on U is the energy.
You're gonna get a power series.
Yeah.
Power is exponential to the energy.
Yeah, so at the end, you're exactly right. This is the power series. So this is equal to e to the minus I over h bar. So here's a little aside over here. If I have a function of an operator acting on that, that is equal to that. Right? So I just have to replace the operator by its eigenvalue. That's a rule, keep in mind. Okay. However, we said that the overall phase of the state is irrelevant, right? Because no probability depends on it. So this is irrelevant. An overall phase. The overall phase doesn't change any probability for any measurement outcome. Which means that the probability of any measurement we do is independent of time. That's why these things are called stationary states. You've heard that term before. In other words, if you are an energy eigenstate, you are a stationary state. Nothing would ever change. You would measure the same thing every time, no matter what time at all. Okay? These were the Bohr orbits. Now, suppose suppose, on the other hand, I am in a superposition of energy eigenstates. Okay? So suppose I had somehow managed to prepare that state at some time that I'm going to call t equals 0. Then what is the state at a later time? Well, it's this. So what is that? Well, I have this on this guy. And what do I get? I get the phase, right? Get e to the minus I e1 t u1 plus c2 e to the minus I e2 t over h bar e2. Is this a stationary state? No. If they're not degenerate, if this energy is different from that energy, then there's a relative phase between that. I mean, I can factor out if I like this one phase. I can do that if I choose to. And what we see here is that there is a relative phase. And that can make all the difference in the world. It can turn the state into a state that's, at a later time, completely orthogonal to the state if this became a minus sign. Right? So what this says is that dynamics depends on relative energies. Note the overall energy of the system doesn't, it can be set wherever I like. What the ground state energy actually is doesn't affect the dynamics. What affects the dynamics is how different energies are relative to some initial fixed energy. Alrighty. One other thing, just as a point, once I have the energy eigenstates, there's an easy way then for me to express the time evolution operator. So I have my time evolution operator. Again, let's set t0 to 0. And let's we have this time independent Hamiltonian. I can express this in the basis of energy eigenstates. Let's take those energies just for the moment to be discrete energies. Okay? Of course, we can also have a continuum. We'll get to that in a little bit. So let's set this for a basis for a Hilbert space. That is to say, they form a resolution of the identity. Again, I'll just for the moment take these to be a discrete set, but this might be an integral. Get to that. So now I want to express this in this basis. What is a representation of U in this basis? Remember, these are eigenstates of the Hamiltonian.
Just a normal eigendecomposition, and the eigenvalues are e to the I, e sub n, e over h bar, t.
There's lots of ways you can get at this. You can put the identity on both sides and then use the oops, excuse me. Because the Hamiltonian is diagonal in this basis, right? That's to say the Hamiltonian is diagonal in this basis with those eigenvalues. Any function of the Hamiltonian is also diagonal in that basis with the eigenvalues just given by those functions. Is that clear? So this is a representation. This thing is sometimes called the propagator because it propagates the system in time. Yes?
Will we go over like spontaneous emission this semester?
Not this semester.
Okay.
But it is a good question, which is, if I'm in an excited state of an atom, which I think about as a energy eigenstate, it's not a stationary state. It decays to the ground state. Well, what that's telling us is that the dynamics of the electron, say, relative to the proton, is not just described by that binding force of the electron to the proton in the hydrogen atom, for example. Because if it were, it would be a stationary state. And the reason is that it's also coupled to other quantum degrees of freedom. And those other quantum degrees of freedom are the electromagnetic vacuum. And so that, if I had a stationary state of the vacuum and the atom, it wouldn't do anything. But it's not a stationary, it's not an eigenstate of the coupling to the vacuum. And it's because of that that it evolves. And the fact that it does so irreversibly and not unitary is related to what we talked about last time, when you have a large number of degrees of freedom and all that stuff. So there's many layers of complication and sophistication on top of this. All right, very good. So I want to now finish with an example. Let's go back to the whiteboard. This in here. All right. So let's look at an example. The only thing we've ever talked about this semester, a spin. Okay? I promise we'll talk about something else soon. So let's talk about a spin, 1/2 particle in a magnetic field. And we'll take this to be a constant magnetic field. Okay? So we've discussed this before. The energy of the spin in the field is related to the interaction between the magnetic moment, dipole moment, and the magnetic field. And that energy is minus magnetic moment dot the magnetic field. That's the Hamiltonian. Now in this case, the magnetic moment is an operator. You take the magnetic field to be classical. Okay, there's my Hamiltonian. And the magnetic dipole moment is proportional to the spin. And that proportionality constant we typically call gamma. This is what's called the gyromagnetic ratio.
Oh, we used to read these two here.
No, that's the G factor. It's a little bit different. This has got the more magneton and other stuff in it. Okay. So this is equal to the following. So let's write this out as minus. So this is minus gamma B dot S, and S is equal to about sigma. Right? So S is 8 over 2 sigma. This is an energy. If this is an energy, and this is h bar, what does this have to have the units of? H bar something is energy.
Per second.
H bar per second, H bar omega, right? H bar omega is energy. So this is a frequency. Energy divided by H bar is frequency. You better know that. And so we'll call it capital omega. It's a frequency. Okay. So my Hamiltonian here, I can write as minus H bar omega over 2 dot sigma. Then let's take the magnetic field to be in the z direction. We'll call the direction of the magnetic field the z direction. That is tradition. Tradition. Okay. And so that tells me then that the Hamiltonian is minus h bar omega over 2 sigma z. So now I ask you, what are the eigenvectors and eigenvalues of the Hamiltonian? What are the stationary states and the energy levels of this Hamiltonian?
Plus minus h bar over 2.
Yeah, that's the eigenvalues, and what are the eigenvectors?
Plus minus z.
Yeah, they're up and down along the z-axis. So the eigenvectors of the Hamiltonian are plus and minus along the z-axis, and the eigenvalues are minus plus h bar omega. Okay. So if I were to draw an energy level diagram of this system, it says that spin up along z is the ground state, and spin down along z is the excited state. And the splitting between them is that, right? This one goes down by h bar omega over 2, and this one goes up by h bar omega over 2. This corresponds to the case where the spin, or mu, and v are aligned. And this corresponds to the case where mu and v are anti-aligned. That's the excited state. The system wants to align the spin, or the magnetic moment. Now, I made an explicit assumption, just a little aside. This will at some point become confusing. that gamma was positive, a positive number, right? If gamma is a negative number, then this flips, right? It's always the case that the magnetic moment, when it's aligned with the magnetic field, is the lower energy. And when the magnetic moment is anton, it's a higher energy. But it's not always the case that the spin and the magnetic moment are in the same direction. Because if it's an electron, they're in the opposite direction. Because the damn electron has negative charge. Because of damn Ben Franklin.
But it won't change the actual edge though.
It just changes what would happen to spin down would be the lower energy. Because spin down would correspond to, see in this case, the spin and the magnetic moment are in the same direction.
If you have spin 3 halves, then gamma becomes important to know, right?
Becomes what?
If you have spin 3 halves, then you need to know what gamma is, right?
Oh, if you have higher spins, I mean, it depends. That's a much more complicated question, is what they are for higher spins. I just wanted to get across the point that when we have to be careful about what this gyromagnetic ratio is when we look at real physical problems. Okay? But with that aside, this is correct. Okay, so I'm just going to here say gamma is greater than 0. Right, so now the question is, let's look at dynamics. Okay, let's suppose at time t equals 0, the state of the system is spin up along x. Okay. What is the state at a later time? Yeah, well, so how do you solve the initial value problem? There's lots of ways to do it, but the simplest way is the following. You decompose the initial state in terms of the eigenstates of the Hamiltonian. That's the first thing you do. So the first thing to do, step 1, decompose the initial state as a superposition of energy eigenstates. So generally that involves, putting in a complete set and doing all that, but you can just read that off because we know that one. This one we've done so many times, you better know this. What is this?
R squared 2 times plus mz down.
Exactly. Okay, so this is a superposition of spin up along z and spin down along z. Okay, and so initially the probability of spin up along z is equal to the probability of spin down along z is 1/2. Okay, what is the state now at a later time? Well, we just did that. So we just apply the propagator to the state. Right? So what is that? Well, this guy picks up the energy of the plus eigenstate. And this guy picks up the phase factor associated with the spin down state. Right? Each one picks up that phase. And that phase is here. I mean, given by those energy levels. So we plug that in. Right? So, what is the probability to be plus z at some later time? It's the same. And because these are stationary states, the probability to be in the eigenstates doesn't change with time. The spectrum of the state relative to its the eigenvalues of the Hamiltonian are not changing with time. But that doesn't mean nothing is changing with time. What about relative to the x basis, which doesn't commute with z? Sigma x and sigma z don't commute. So at a later time, something will happen. Well, there's lots of ways to look at that. What we want to know is, let's express the state of the later time in basis up and down along x. We could do that. So, I'm just going to, I can put in a complete set of states, or I can just remember that up along z is a superposition of up along x and down along x. And spin down along z is a superposition with the other sign. I just substituted it. That's one way of doing it. Lots of ways of doing it. So this then is equal to e to the I plus e to the minus I over 2 spin up along x plus e to the I omega over 2 minus e to the minus I omega t over 2 over 2 down along z. I mean x. Which is sine and cosine. So what we have here thus is that with respect to the x basis, we have the cosine of omega t over 2 spin up along x plus I sine spin down along x. So what is the probability to be spin up along x at some later time?
Cosine squared.
Cosine squared. Excellent. Good job. And similarly for down, it's sine squared. Or 1 minus cos omega over 2, this is the plus, and this is the minus. We're using some trigonometric identities. So if I were to plot this, what I see is that as a function of time, the probability as a function of time starts out simply. This is the probability to be up along x, and this is the probability to be down along x. It started out spin up along x, and then it becomes spin up, it becomes spin down along x, right? Where, well, this should be all at the same amplitude. And this is 2, it's in a linear superposition of the two. Yeah,
I mean, but it's not that the particle actually rotates.
it is. It's exactly what's happening. So what it says is, let's just complete this discussion by saying the following thing. What is the expected value of, say, the spin along the x direction as a function of time?
0?
Well, let's note that at any fixed time, and not averaged over time,
okay.
right? This is equal to, by definition, the sum over the energy eigenvalue, the spin eigenvalues, right? Times let's put it this way. This is equal to h bar over 2 times the probability to be spin up along x at time t minus h bar over 2 the probability to be spin down along x. There's lots of ways to do this problem, right? I mean, this is just, I could write it out more explicitly. This is equal to this operator, this matrix element. That's the expectation value. This is 1 plus cosh. This is 1 minus cosh. So this is equal to cosine omega t. The mean value of the spin is cosine. If you did the y, we times h bar over 2. And the y component, if you did the same thing, you would find sine. So what's happening in this problem is exactly what Zeke suggested. Here's the z, here's the magnetic field in the z direction. We started the spin along the x-axis, right? So here, so this is the x-axis, this is the y-axis. We started the spin here. At time t equals 0, the expected value was here. At later times, it's here. And it's precessing. This is what we call Larmor precession. In fact, it's exactly what you would see classically. If you put a magnetic moment in a magnetic field, and you put it in a direction other than it, it will precess around that. If I put it like this, it would precess like that, like a gyroscope. And the quantum evolution is exactly the same as far as the mean value goes. Of course, it's not a classical spin that's in a certain direction, because if I measure it, I'd still have this, if I measured this bit, half the time I'll find it here and half the time I'll find it there. But the point of the matter is the mean value, the expected value, rotates. Now, of course, at all times, there's a 50-50 chance of finding it here or here. Because all the states in this equator are 50% this and 50% that. Weird. All right. To be continued. If you didn't pick up your homework, I have a few left here. And you can take it all.